So we'll continue our discussion on robot modeling, discussing about inverse kinematics this week, because inverse is better, and we'll see why. Just to be again on the same ground, we'll do a little bit of background, discussing about what we talked about last 5 weeks, very briefly, so that we can better grasp what we're going to talk today. Then we'll talk about inverse kinematics, how we solve it, and see some example, basically. All right, so previous weeks we talked about forward kinematics mainly. Right, we talked about these modified DH parameters and how we place axes on the robot, on the joints, so that we calculate the forward kinematics. And we saw that basically the kinematics from one joint to the next, they have a standard form. And we used this information to construct last week the Jacobian, which gives us the relationship between joint velocities and end effector velocities. So basically we are not yet halfway, but close there. Talked about the kinematics part. And today we'll move on to the last part of the kinematics, and next week we'll complete it when talking about trajectories. All right. So let's really understand what forward kinematics is once again, right? So it's basically a transformation matrix, this 4x4 matrix that tells me what is the pose of the end effector of the robot, or what is the pose of frame attached at the end effector of the robot, to be more academic, with respect to a reference frame. I didn't put a reference frame here, but you can imagine it. Right? And we saw that these 4x4 matrices, they capture all the information about the orientation of this frame with respect to the reference frame and the position of the origin. Right? Right. The orientation was in this 3x3 submatrix presented here, and the position of the origin of the frame is the last 3 elements. Correct? We saw that this is a function of Q, right? So this orientation and position depends on joint positions, right? On joint coordinates, as we call it, which we denote with Q, which is a vector of all the joint coordinates. If we have 5 coordinates, Q will be a vector of 5 elements. Right? If we have 5 joints. Kids are very happy to be back from holiday. It was holiday last week. All right. So these numbers here, they depend from Q1, Q2, Q3, Q4. Right? Now, how many of these numbers are independent from each other? We have basically, it's a 4x4, so 60 numbers, but these 4, they always have this 0, 0, 0, 1 values. So we're talking about 12 numbers. These 9 here, plus these 3 here. How many of these are independent? 9. Can I put whatever values I want there? No? 9? 9 the number, or 9 German for no? The position is dependent on the XYZ. Well, yeah, these represent the position of the origin of this frame with respect to the reference frame, right? Can I put whatever values I want there? Overall, can this, forget about the robot for now. I just have a frame and I move it around. Can the position take any value I want? Can this be basically wherever I want it to be? Forget about the robot. If we're talking about the robot, yes, we have some limitations here, but generally it can be wherever I want it to be, right? And I can change each of these 3 independently, right? It can be anywhere on X, anywhere on Y, on Z, how I like it. Of course, when we're talking about the robot, it cannot be wherever, and we'll see about that later. Yeah. What about the other 9 numbers? can I change those 9 numbers and put whatever values I want on each one of them?
No, they are interdependent.
They're dependent,
Yeah.
right? Why?
Because when we rotate something, it can modify the value of the other rotation.
When we modify what?
For example, x with respect to y is dependent on y with respect to x.
So basically you're talking about these two values?
Yeah.
Why? Are they dependent?
I said they are dependent.
They are dependent, yeah. Why are they dependent?
Because
What kind of dependency they have?
But
Inverse? So whatever value I have for x, y, I will have the inverse for y, x.
negative,
Negative?
I think so.
So basically you're saying that this is a diagonal matrix, that, you know, it's a symmetric matrix, sorry, on the diagonal, that whatever I have on up, I have the inverse.
Maybe.
What are these numbers? What do these numbers represent when talking about this?
Rotation.
All right, but more specifically, what is this x, y, z?
Orientation of one axis with respect to the other.
Orientation of, so these ones I mentioned, x, y, z, is the orientation of this axis, we say, okay, but more specifically is the 3 coordinates of the tip of this axis with respect to the reference frame, if they have the same origin, right? So this is a vector, and it will have some coordinates, right? So these are these 3 numbers. What do we know about this vector? Sorry? It's length 1, right? So I cannot put any value I want. I cannot put it here, right? It has to have length 1. So that's one constraint. And I know this for all the 3 vectors. They all have length 1. Right? So basically, what I know is that, what does length 1 mean? You know, if I have the 3 coordinates, if I take the square root of the sum of the squares for each one of the vectors, they have to have length 1. That's the norm, you know, the Euclidean distance, whatever, how you call it. Right, so that's a constraint. Imagine that if I take the first one, if I know x, y, and I know it has to be equal to 1, the sum of the squares, then I can, xz, I don't have any freedom to choose anymore. Right? So if I know that I have to respect this relationship, xz equals to 1, square root, but since it's 1, I can ignore this. Basically, if I have some value for x, sorry? Yes, I know you said you have OCD. You noticed immediately. All right, so yeah, if I give some values for x, and xy, then this will define the value for xz, right? So I cannot change this one independently if I choose these 2, right? That's what it means that, you know, from these 3 numbers, only 2 of them are independent. I can choose 2 of them, and that will define the value of the 3rd one, because they have to respect this relationship, right? And it's the same for the other 2 axes as well. So I have basically these 3 constraints, right? Each one is a constraint. This has to be equal to 1, this has to be equal to 1, this has to be equal to 1, right? Good. So from these 9 numbers, only 6 of them are independent. Because if I define these 2, then this is not independent, it's dependent. The same thing here, the same thing here. Right? So 6 of them are independent. All right, do I have any other constraints here? What do I know about these 3 axes with relationship to each other? They're perpendicular to each other, and they follow the cross product, basically, that x cross product y is z, right? Y cross product z x, and z cross product x is y, right? So they have to be perpendicular. So what does this tell me? Like, if I place somewhere my x-axis, right? This defines, this constrains where the z can be. It can be here, it can be somewhere around here, right? So this gives me, basically, if I place the x-axis somewhere, I have 1 degree of freedom for the z-axis. The moment I define, so I define x, y, x, x, let's say, that defines x, z, okay? The moment I choose z, x, for instance, then I have defined completely where z, y will be, and therefore z, 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 right? Because I just have one way I can rotate here. Right? And the moment I put the z-axis, then I don't have any more freedom to choose the y-axis. Right? It has to be perpendicular to these two. It has to have length 1. So that's it. So basically I have these constraints as well, which tells me the cross product between x and y is z, between y and z is x. I could write as well that between z and x is y, but this is basically a circular constraint. It's not an extra constraint. It gets derived from these two. All right, so I have 2 more constraints. This means that from these 9 numbers, how many of these numbers are independent in the end? How many constraints I have? 1, 2, 3, 4, 5. It's not 4. So we said from these ones we have 6 constraints. 6 independent variables, and then from these ones we have basically 1 more. In the end we have 3 independent variables, right? So the moment I choose, let's say, the direction of x by choosing 2 numbers, right? We said 2 numbers are enough to define x direction, right? Because the third one is not defined, right? And then I have 1 more thing to choose for the direction of z or x or y, sorry, right? 1 more variable. So when I have these 3 variables, I have defined, all the other numbers, basically.
And also the translation, they're independent as well.
Sorry?
And the translation as well, they're independent.
The translation is dependent. Now we're talking just about the orientation, right? The translation, we say that it can be wherever. Right? We don't have any constraints on the position of this. But I have constraints on the orientation, and this is basically this 5 constraints. All right, good. So this gives me 3 basically independent variables for the orientation and 3 for the translation, right? So in the end we have these 6 independent variables, which is our 6 degrees of freedom, like how many, 3 different ways to rotate and 3 different ways to translate. All right. We said many times that forward kinematics is a function of joint coordinates, q, that basically it gets this as an input, the joint coordinates, and what it gives us, what it returns us as an answer is the pose of the end effector. If I know my q, I know where is the end effector. Right, so we write it like this. It gives me pose as position and orientation. Orientation can be this 3x3 matrix, but we can also write it, since we have 3 variables that are independent, we can write it as what we typically call the Euler angles, right? Which represents the orientation matrix using 3 rotations. The type of rotations that we have can vary, but typically for robotics we use a rotation around z by an angle psi, a rotation around y by an angle theta, and a rotation around x with an angle phi. Right? We can read this as rotation around z multiplied from the right, rotation y multiplied from the right, rotation around x, or the other way around, rotation around x multiplied from the left. I mean, your left is my right, right? But basically, the resulting orientation will be something like this. So we take this orientation described as projections of this axis on the reference frame, and we rewrite it as basically orientation described by 3 rotations, one after the other. which we typically call the Euler angles. So in the end, my forward kinematics can give me back position on XYZ for the origin of the frame and 3 rotations, phi, theta, and psi. Right. This is forward kinematics. Now let's talk about inverse kinematics, and I typically saw this video from Boston Dynamics that might be too old for you. It's basically showing Spot doing some dance moves. Have you seen this? Yes? It's like, I don't know, 5 years ago. Okay, I'll not play it all, maybe at the break. Well, what's the robot doing here? It's doing some moves. Right, it's dancing, okay, but it could be anything. It could be welding, it could be opening doors, whatever, right? But how is it doing with what we know so far? Can we actually do this kind of movements using forward kinematics? No, why not?
To find the end position of the joint, for example, for the leg, to know, okay, in that you need to be here.
All right.
To make some reverse engineering of
we need to do something reverse of that, right? Because forward kinematics tells me if I know the joint, where is my end effector, right? But, you know, I'm actually controlling the joints for the end effector. Like, this is my control input. So I want to figure out if I want to do this kind of movements or any kind of movement. Okay, I have a target. I have a specific motion that, or a place that the leg or the arm needs to go. And I need to figure out, okay, where should my joints be in order to have that, that target? And using just forward kinematics, that would mean, I know, trial and error, like trying different angles. I'll try to demonstrate here, trying different angles until I reach, you know, my target. Let's say the target is down there, so I have to wiggle around until I manage to, you know, reach the pose I actually want to. I'm not putting them very close because they're gonna snap, the magnets. Right. Instead of using forward kinematics, we basically invert the model and we try to define what we call the inverse kinematics, right? Which is basically the inverse function of the forward kinematics, where now the input is pose. We have a target pose, or I don't know what the robot was doing. That's the input, and what the function returns is the joint angles that I need in order to reach that pose. So it will return me, I don't know, the joint values that I have now, the joint coordinates I have now, right? If this is the target I have. Or another way to say, to call it the function that calculates joint coordinates for a specific pose, right? Forward kinematics, inverse kinematics is basically one the inverse of the other. Makes sense, right? So I said in the beginning that, okay, inverse is better. Why inverse model is more useful in a way for robotics?
I usually know where I want to. It is more predictable.
Not more predictable, but I usually know what the robot should interact with, right? Where is the piece that it should pick? What's the door that it has to open, or where should it, go towards? So we have a target, usually in the physical world, right? And we want to translate that into what we are actually controlling for the robot. All right, but it's also more difficult to derive. Why? First of all, because we first have to define the forward kinematics in order to do the inverse kinematics. But So yeah, if I have a robot, then I have first to do the forward kinematics in order to calculate inverse kinematics. But we also have weird situations, like inverse kinematic might have multiple solutions. It's basically we're trying to invert nonlinear functions, because here the forward kinematic is a nonlinear function of cosinus, sinuses, trigonometry multiplied, added together, and whatnot. And we have a lot of, complications inverting these functions. Right here, I try to present a situation where I basically, for the same target pose, right? You can imagine I have a target pose here. I can have multiple solutions. Right? There's more than just one way to reach this pose, maybe. No? Okay. For this specific, you see here, right? I can have different joint coordinates that result in the same, more or less, pose, right? So then, which one do I choose eventually?
The one that does less movement.
We're going to talk about it next week when we talk about trajectories, but yeah, I just give you a hint of the complications arising from inverse kinematics. All right. The inverse model can be tricky even for simple models. We'll see this example today, and we'll solve the inverse kinematics for this one, and we'll see that it's going to take us basically some time. So you can imagine if we have more degrees of more joints and so on, it gets more and more complicated, right? So let's see, how do we actually derive it? So we start by taking the forward kinematics of the robot. So we have this 2 degree of freedom robot with this forward kinematics, right? And we equate it to the general form of a 4x4 transformation matrix, right? Or if we want to work with Euler, then we use basically this form. And then this is basically a system of equations, right? We have 12 equations for the 12 positions on the matrix, right? The left side is equal to the right side. So each element, let's say this one will be equal to this one. This element here will be equal to this one, and so on and so forth. The position on X will be equal to this element here, right? So I can write these equations. So this is the same equation as here, but I have basically written it separately. Right? Each element equated to from the left to the right side. Right, so what do I have here? I have cosinus of Q1 plus Q2 equals to this XX projection. And if you see, it's also equal to this YY projection, right? Or if we write the Euler representation, it's basically this equals to this. Because here I have this element, and here I have this element. All right? That's what I was saying earlier, right? That we might have multiple solutions than one, right? So that's what I was trying to demonstrate here. Like you see here, for the same target pose, I don't need the second matrix here, but I can basically have different joint coordinates resulting in the same pose, right? This means that I have multiple solutions for this target pose. Okay, it's wiggling a bit, but I think you get the picture, right? And we'll see it also from the equations that we might have multiple solutions. Yes, tell me.
I would wait for us to tell you that.
All right, but we might have different solutions. Yes, you can see it even here, right? What does this? So let's complete this one. So the second line is basically derived from this element and this element, which is equal to x, y, and yx. So in this case, it is what you were saying, like it's one minus the other, but it doesn't always happen like this. Like for instance, xz and zx is also one negative to the other, okay, but it's not always like this. Right. So from these two we get this equation, which is basically sinus Q1 plus Q2 equals to x, y, or minus yx. or if I look at the Euler side, it's basically this one. Right, and the three positions, we can see that z will always be 0, pz, right, because I'm moving on the screen. And px will be this one, pz will be this one. Right. Now, how much freedom do we have? This relates to the discussion with the degrees of freedom. What did we say when we were talking about degrees of freedom, when we were talking about the robot model? How do we add degrees of freedom in the robot?
Adding more joints.
Adding joints. So for this robot, how many degrees of freedom did we say we have? We have 2, right? We kind of empirically showed it there. Like, why do we have 2? Because we can move basically one of the two positions and one orientation that is possible on the 2 dimensions. Two of these we can move independently, right? Let's have a look at the equations here and try to get a feeling a bit more equation side, right? So let's take the first 2 equations. Are they independent, one from the other? So can I set xx independently from y? I cannot, for sure, because they have exactly the same form, right? So these 2 are tightly together. Basically, what does this tell me? xx and xy, and sorry, yy is what? Is the projection of x on x and the projection of y on y. And basically, you see that no matter how I rotate, this projection of x on x and y on y will always be the same, right? So this line here and this line length here will be the same. It will be what? Cosinus of this angle. Correct? If I rotate it more, it's going to be again the same. Because these 2 basically move together. I cannot move one without moving the other. Alright, so that's what the first equation tells me. What does the second equation tell me? This is the other projection. So now I have x, y, oops, sorry, and yx, right? What's the first one? Now it's this projection for x, so the projection of x on y, right? And the projection of y on x. So this distance and this distance. I'll take this away so you see it. So if this rotates like this, it's going to be basically this one with this one, which will be the same if the vectors have the same length. Here, I mean, these ones don't really have the same length. That's why maybe it's not super clear. But you know, this projection will be the same as this one if this is 90 degrees. Because why? This angle here is the same as this angle here, because the sides are perpendicular. All right. So these 2 are also connected, and it's with a minus. Like this projection is minus this projection. Like this goes on the negative side. You see the minus side? Okay. So these again move together. And obviously, or not so obviously, we see that, okay, xx is not dependent from yy, and xy is not independent from yx. Now, are these 2 independent? Is xx and xy independent? Can I change xx without changing xy? No, right? You can see it from the equation, like the moment I change xx, I set some values for q1 and q2, I use the same values for calculating xy. Right? What's going on here? Basically, I'll make this a bit bigger. What is xx? xx is this one, and this is xy. Right? Obviously they're connected, you know, they only depend on this angle. If I know this angle and this length, which is 1, I can calculate both of them. Right? I cannot change this one without changing this one, because I have a fixed length. Right? So we start getting a feeling on the equation side, okay, that I cannot change all the orientations independently. All right. Would xx and px be independent? Can I change px, for instance, without changing xx? And how could I do that? And I write the equations here so we have them. X and L2 cos Q1 plus Q2 plus L1 cosinus of Q1 equals Px. Can I change Q1 and Q2 so that xx changes and px doesn't change, or the other way around? I think it's easier if we think, can I change px by wiggling with Q1 and Q2 and xx shouldn't change? No? We can? How?
We thought before that there are multiple combinations of angles to get to the same point, so if we get the right angles, x remains the same and px changes.
Yeah, so I can wiggle these two. So let's say I make this increase by the same amount that this one decreases. This sum will be the same. So this value will be the same. But then because I change Q1, I will have a different px. So I can do it, right? With some limits, of course. But yeah, I have this possibility. So these two are not independent. They're not dependent. They are independent to some extent. All right. Can I do the same thing here? Sin Q1, Py. So with these two I can do the same thing, right? I can change Q1, Q2, so these two are also independent. Are these two independent? Can I change Px without changing Py? Can you think of an example that I can change? Let's put some values. Let's say Q1 is 0. And Q1 is 0. And Q1 is 0. And Q2 is what?
90.
Sorry?
90 degrees.
Is this a good example actually? Not sure. Let's say it's 90 degrees. Pi over 2. All right. What do I get for Px and for Py?
Px is L2 cos pi over 2.
So this will be what?
For px.
For Px will be
L1.
L1. Okay. For Py?
Minus L2.
Y minus L2?
No, L2.
Okay, L2. All right. I think I'm shooting myself on the leg now, but yeah, can we think of a way that we keep this to be L2 and that this one is not L1? Yeah, I guess it depends on L1 and L2.
If we use pi minus pi over 2.
Sorry, if we use?
Pi minus pi over 2.
For which one? So pi minus pi over 2. So this will be pi. Don't, yeah, all right, good one. So this is pi minus pi over 2. This is pi. What do I get here? Pi minus pi over 2, pi over 2, which was the same as before, right? 0 and pi, minus L1, right? Pi minus pi over 2 is the same as thing here. So this will be L2. This one, 0. So this is still L2, right? Good one.
Can we solve this other ways than just guessing?
To show that they're independent,
Yeah.
because that's basically where we're trying to get. It's tricky with non-linear functions, but yeah, if you talk to a mathematician, probably he will say yes. But yeah, here I'm just providing, empirical proof that yeah, these two are in some situations they're independent from each other because we can change one without the other. If we can prove it, with mathematical rigor, probably we can, but I don't know how. Right.
So just let's say if we get a robot, we don't know much about it. We have to figure out what is independent and what not.
How do you do it?
How do you want?
How do you figure out which are the independent degrees of freedom? That's what you're asking, right? Yes.
Just play with the values
And yes, I don't know. I'll try to find an answer to this. But the software would be again numerical, I don't know,
maybe
simulations and so on. Now, this thing will depend also on the joint configuration. That's why it's complex as well. Because you have, as we talked last week as well, you have different degrees of freedom when, I don't know, in some configurations, let's say here, oops, I can change, I messed up. I can change all degrees of freedom, I don't know, independently, but if I'm in this configuration singularity, then I stop being able to change x and y independently, right? So in that sense, I'm saying that it depends on the configuration. I start messing things too much. Because these equations will stop being independent in some situations, the same equations, right? Okay. What I want you to remember is that, okay, what do we mean by degrees of freedom is how many of these equations we have independent. Right? Why I'm saying that since it's a nonlinear system, it's difficult to answer this question. How could we answer this question if it was a linear system? We could write a matrix. We could write this in matrix form, right? And then if the matrix, the rank of the matrix was equal to the size of it, then it would be basically fully independent, right? If it wasn't, then some equation would not be independent. But we cannot write this in matrix form, right? You remember from these things from linear algebra? It's basically what we said last week as well with the Jacobian when inverting it. We can invert it as long as the rank is equal to the size. It's the same thing with systems, right? If the rank is equal to the size of the system, then all the equations are independent. If not, then is equal how many equations are independent is equal to the rank.
then
Right?
the determinant should be different from 0.
Yes, if it is 0, then the rank is not the same as the size of the matrix. All right? Okay. So how do we solve the inverse kinematics? Because that's what we're trying to do. And what do we mean by solving? We want to reach this equation that I mentioned, right, where we have some function of pose phi, theta, and psi, which gives me joint coordinates. Right, that's what I mean when I say solve the inverse kinematics. Means I want these functions. And in the end, I will want one function for each joint. Right? Or how many joints I have. Now, here's the detail and why I insist on the degrees of freedom. We want the inputs to be basically the degrees of freedom that I want to solve the inverse kinematics model for. Right? We saw that for this example, we have basically 2 degrees of freedom. But we have 4 equations or 5 equations or 3 equations, depends how you count them. But let's say we have these 5 equations. But some are redundant, like the last one, doesn't tell me anything. So it doesn't make sense to solve the inverse kinematics for pz, right? Because it will never tell me anything about q1 and q2. Right? There's no q1 and q2 involved here. Right? It's 0 as pz. It's like a, it doesn't help me anyway, right? And then from the others, we only know that only 2 of them are independent. So it doesn't make sense to try to solve the inverse kinematics for 3 or 4 of them. Right? Take the first one as example. Right? I cannot solve the inverse kinematics if I take the first 2 of them because they're dependent on one on each other. Right? I will have an answer for the sum of q1 and q2, for instance, but I will not know how to split q1 or q2. Right? So at this step, we need to choose. We need to know how many degrees of freedom the robot has. In your case, it will be given, so you don't have to, figure it out. And then choose the degrees of freedom for which I want to solve the inverse kinematics for. Meaning, when controlling my robot, do I care about position on x and position on y? Do I care position on x and orientation? Do I care about position on y and orientation? And I have to choose, right, at this step. Do I care about position or position and some orientation? Okay? When I ask you to solve the inverse kinematics for robots that don't have 6 degrees of freedom, and we cannot solve for all degrees of freedom, then I will specifically say solve the inverse kinematics for this and that orientation or position. All right? Good. So when we do that, let's say we want, in this example, to solve for the position of the robot. We care about the position of the robot and we don't care about the orientation. I don't know, it's a pick and place, whatever, and we care about accurately positioning it on x and y, and we don't care about the orientation. Right? So when we say this, then basically I boil this down to solving these equations for these degrees of freedom. Right? I want to figure out q1, what is the value for q1 for different values of position on x and y. What is the value of q2 for different positions on x and y. All right? So I'm trying to come up with these equations. And we'll see we have 3 main types of solutions: analytical, geometric, or what we call numerical solutions. All right? We'll see analytical and geometric solutions for this example, and then in the lab you will basically solve it using numerical solutions. Right. So what we're trying to do here is take the 2 equations for the 2 degrees of freedom that we chose, basically these 2, the last ones, and we're trying to invert them. Solve these equations for q1 and q2. Right? Basically, by moving things left and right. Yes, so we're trying to come up with equations or functions for each joint that only depend on the end effector pose variables that we chose for the inverse kinematics. We always start by equating the forward kinematics with a general homogeneous matrix. So basically this part that I showed here, right? And taking the equations for the degrees of freedom that we care. In this case, position on x and y. And then we're trying to look at the equations and figure out what can be isolated, if something can be simplified, either by division or by multiplication or trigonometry or different, I don't know, tricks. We'll see in the example what kind of tricks we use. And we hope that we'll be able to, isolate Q1 and Q2 as a function of position. If that doesn't work, another trick we're using is that we take again this equation of the forward kinematics with the general homogeneous transformation matrix, and we multiply, which is basically multiplications of the subsequent joint transformations, right? And we either multiply from the left with the first transformation, the inverse of the first transformation, both the forward kinematics multiplication from the left with an inverse and the general homogeneous transformation matrix with the same, and we try to isolate again. Basically, it's as if calculating the inverse kinematics until the joint before the end, but both the forward kinematics and the general homogeneous transformation matrix, or we do we neglect the first joint, right? Because we multiply with the first transformation, or we multiply from the right with the last transformation. So then we neglect the final transformation. And we try to isolate again. We'll see briefly at the end this example.
What question regarding RG is not the same as R0 to M, or what's the...
This one is RG, and this is the R0 to 3 in this case, right? So what will happen here is I would take the last transformation, for instance, and multiply both of them. So then I will have a simpler form on the left because I will not have the last transformation, but I will have a more complex on the right side. And this might help again identify some relationship that can be simplified. All right. Good. Next step is to solve the example. Maybe we should take a break now, since it's almost time to break, and then we dive into the example. Right, but keep it short, the break. 10 minutes maximum.